We'll find some way to figure out the desktop issue, but I believe the Windows laptops work as of now, right? But just the desktops still have issues. IT installed Vivado last week, but it's able to run simulations, but not programming to the FPGA. Okay, so a few things for the lab, really quick. If you cannot program, then that'll be a problem. Yeah. Good. First, when you see a code like this, make sure that you change it back to lowercase LED. Because the switches, SW, which is remember I told you in the morning the test bench for the FPGA experiment is the board itself. So the FPGA board is the test bench, and SW is the keyword in the constraint file. It's the switches. There are 16 switches. And for LEDs, there are 16 LEDs, so it's lowercase LED in your constraint file. Okay, you want to change it back to lowercase LED. You can just use individual switches for the connection. You don't have to use all of them, but you declare all of them. So later in the code, you can use anyone that has been declared in the port list. So there are two different types of files. So the bit file, let me show you if I can see the bit file window somewhere. None of the snapshots show the bit file, but there's if you open it up, you can see on the bottom left corner, there's a generate bit stream. That's the bit file. That's usually what we use. Okay, the .bit file, right? That's a regular file being programmed to the board through the JTAG port, which is one of the ports on the board. So just follow the regular process. We're programming the board using the bit file. However, if you unplug it, all the code will be gone. Okay, it's volatile. So in order to keep the communication between the code and the chip, the IP chip, you need to download the bin file. It's a different format. Let me show you over here. Okay. So scroll down. Okay, so here's the settings. These settings. So check the bin file. So it's able to generate the bin file as well. bin, the bin file. And so both files will be generated through that generate bit stream. And eventually you set up this guy. This configuration is important. Okay? So this one defines that communication between the memory chip, which is SPI. So SPI has 4 ports. Did the microcontroller cover SPI? I don't. Not yet. Okay, so we will cover this later this semester about the protocol. So there's a chip. I think this guy, SPI flash. It's onboard memory. If you flip the board, you can see it's at the bottom. On the bottom layer, there's a little chip, black square, which is the memory file. So the bin file will be stored in the flash memory, and eventually, as long as you power it on, it's able to communicate between the memory and the FPGA and to deliver that code, the bin file to the FPGA. So in that case, you are not losing your code. So it's going to be stored in a non-volatile memory on the board. So the communication between them is SPI. That's why during the configuration, you need to check this box. So select that port for the communication between the memory and the FPGA. So we are not really optimizing the design, but eventually all these digital blocks we don't really care about because it's so tiny. So you can skip, just click OK to skip this step. So when you are trying to generate all these programming files, if you don't want to click all these steps, starting from run synthesis and implementation, and then eventually go to generate bitstream, you can directly just click generate bitstream. It's going to go through all these synthesis and implementation automatically. So it's a little bit shortcut to simplify the procedure a little bit. You can see in the log file, both bit and bin files are being generated. That's what you want to see here. So when you program it, so open the hotwire, right? Open the hotwire settings, like what I'm showing over here. Open hotwire manager, open new target. So it's making a connection to your FPGA board. And you program the device, you find out the bit file, and you program, okay? That's the first method of programming it. And the second one is program through the memory. So you can see this little memory chip is ready over here. Okay, it's being detected and being listed under here is this window, the hotwire window. And you right click, you can add that configuration memory file, which is a bin file. I'll add the chip first, so select correct chip. That's the name of the memory chip. That's the name of the memory chip. You can see it's a SPI port with the memory. So find out this name of the memory, add, okay, add, and then click these three dots, and eventually it will open up the window and to let you select the bin file that was just generated. So the bin file will be stored in the memory. It's non-volatile. It's not won't be gone. So it will store there forever. Okay. So in that case, you can keep that communication between the memory chip and the FPGA. So you are not losing any. You are not losing the code because of program. So how do we do that? So when you are programming, you don't. So some of the statements, some of the comments in the tutorial says you have to keep, when you're programming, you have to keep the jumper at the JTAG port, but eventually it's probably not the case. So when you are programming, it's okay, it's fine. So the jumper is on the top, which is fine. So this is what I did. Okay, so just for safe, just keep whatever I have when you are programming it. Have these two jumpers at the bottom and these two jumpers on the top. Program it, and once it's programmed, you can switch this jumper to SPI. So I think it shows you how to do it. I cannot read the label. Okay, so over here, see, QSPI. There are three different options. By moving the jumper on the top is the QSPI option. Makes the connection of the SPI ports. And JTAG is the second option, and USB the third option. So move it to the top. So selecting the QSPI. And then you press this button really quick. You press it. It's going to program your FPGA using that chip. Okay? It's going to directly program it using the chips. Bin file. So it shows every single step in the tutorial. Just follow. Okay, just follow. Okay, so the difference is if you program it using the bit file, right? So the USB, because the FPGA board is being powered up by the USB cable, which is providing 5 volts to it, right? So program it. You unplug it, unpower it, power it off. Eventually the whatever being programmed over there will be gone. So if you do it, use the bin file, you turn it off and you turn it back on, it will still be there. Okay, it stays there. So that's the difference. Any other things we want to talk about? All right, running LEDs. There will be a experiment added to the bottom. Shows you the running LEDs of the FPGA. So there's a little delay. You have to program the time delay here by yourself. You can see it's cycling through these 4 LEDs, and eventually it goes back. And I think I'm adding a reset switch So no matter where the LED is at, if I turn the switch, it's gonna reset it. So the LED goes back to the one on the right hand side. It resets all the LEDs to the initial state. Okay, that's the goal, right? So take a further look at it for a few more times. Did I show a reset? I didn't show a reset. Okay. But I added to the code. You can see this is the module. This is the module for the Verilog. So take a look at it. Before we talk about it, take a look at it. So here's the module running LED. Input something, right? Getting crossed out. Output LEDs. Parameter is a constant. I set up a really big constant. It's a decimal number, okay? It's a 32-bit decimal number. But you are counting this number of digits, it's not 32 bits. Some programming basics, right? So this is a decimal number followed by D, right? It's decimal number. If you convert it to 32 binary bits. So this number has to be smaller than that 32 binary bits. The largest number we can represent by 32 binary bits. You know what I mean? So you are generating a 32 binary bits of memory space to hold this decimal number, which is 100 million. Right? Okay, it's just declaring a constant, 100 million, but you need a 32 binary bits for the space to hold it. And then I generate a counter. It's a 32-bit counter. So the the goal of the counter is to count up to this counter max. So the counter's max number. Whenever it reaches this number, it do something. So for the always statement, it's either the rising edge of the clock. So whenever the rising edge arrives, it updates everything in this block. Or a negative edge of the rest of the reset. It's a switch, I believe. It's a switch or button, depending on where I connect it to, right? I don't have a top module here for you guys, a test bench, but you can connect it to, for example, button. If reset is 1, then do the following. Okay, I think I used the switch. Okay. So begin, so for the code, if reset is 1, then do the following. If reset is not 1, okay, so if this is not changing to 1, then count it, okay, count it. So how do we count it? Else if counter equals what? Equals the max, right? So when counter equals the max, reset it, okay? Put it back to 0. So when the counter spends so much time to count it towards 100 million, so whenever it reaches that number, it goes back to 0. The reason for that is the FPGA has a really fast clock, which is 100 megahertz over here. That's why we want to count it to 100 million. It's a little bit different from 100 mega, right? 100 megahertz, is that 100 million cycles per second? It could be a little bit different. I think so too, yeah. So it's basically 1 second, right? So 100 megahertz will have 100 million cycles per second. So that means whenever it reaches 100 million, it takes 1 second to reach there, right? Then I reset it. So it's able to run another cycle, start counting again. So what I'm doing here is I'm shifting the MSB to the LSB. Did you see this technique over here? It's very important. We are going to use this technique a lot in the future. So how to shift it? How to do the running LED? So LED 3 was the MSB, but I shift the MSB to the right. It's basically shifting everything to the left, right? So I'm moving from bit 0 to bit 2. I'm moving these 3 bits to the left by 1 bit, by 1 digit. So eventually there's nothing else on the left. So eventually bit 2 becomes MSB. Bit 3 becomes LSB. So it's shifting to the left, shifting back. MSB shifting back to the right. And eventually assign the shifted results to the LED variable. One very quick question. Am I shifting the test benches keywords, or I'm just shifting something else in here? So by shifting the LEDs, right? Remember I told you guys in the constraint file, the LEDs are keywords and it's case sensitive. So it has to be lowercase LEDs, right? So am I shifting the real LED keywords of the FPGA or not? Why? It's a module, right? Okay. Are you allowed to shift the keywords? No. You have to have an intermediate variable in your test bench. If in the test bench you have to shift something, keep in mind, it has to be some intermediate variable in there. You cannot directly shift the keywords, data. Just to let you guys know. So here's fine because it's still within the module. It just has the same name. I just have the same name as the ones from the FPGA. It's the LED, okay? If it's not reaching 100 million yet, you want to count by 1. So increment it by 1, right? So it's going to be count plus 1 and assigned to count, right? Why do I cross it off? Yeah. Just count it by 1, right? So eventually it counted towards 100 million. It takes 1 second. So this running LED takes 1 second for each shift. And for the assignment, if you look at the last assignment, number 4, okay, similar to the running LED examples, and run it on the 16 LEDs. It's very simple changes, right? And must have the reset function. Do I have the reset? Yes, I do have the reset. So I have the reset function. You can use a switch to reset it, or you can use the push button to reset it. Did I show the push button there at all? Let me show you really quick. It's over here, here. Make it bigger. Where are the buttons? Here, button C. So button C is the center button. Button U, the upper button, lower button, and right button and lower down D. What is D? What does D mean? You can see the labels on the board. Left is left. Yeah, left, right, and down. Right, up and down, center. So there are 5 buttons. So I have to uncomment this piece of code in the constraint file in order to use the buttons, right? And those JCs are GPLs. We're not using them. These are ADC ports. I'll use the ADCs later in the semester. What's that? Outside of that. So the ADCs, VGAs will be probably 2 weeks, 3 weeks from now. RX, TX will be the UART. PS through the USB. SPI. Yeah, that's it. That's everything about FPGA. All the available resources on the FPGA. Okay, these are 7-segment display enable pins. We'll talk about that next week. 7-segment display LEDs. Okay. Yeah, switches and LEDs. That's it. All right. Let's go back here. So these are easy, right? Just generating extra OR gates, very similar to the AND gates, and implement it on the FPGA using switches and LEDs to verify it. And program it, use the SPI memory. And this one, keep in mind, one of the modules will be on the quiz, okay, on Thursday. So for the 421 marks, take a look at this. So this means is S1 0 or 1. Okay, if S1 is 1, it's picking up this guy. I think I'm right? Yeah. So if S1 is 1, it's picking up the one on the left. If S1 is 0, it's picking up the one on the right. Then it's doing a nested statement. Okay. So then you do another one here. If S0 is 0, it's picking up D3. If S0 is 1, it's picking up. Oh, if F0 is 1, it's picking up D3. If S0 is 0, it's picking up D2. So in that case, if I'm having 1 1, so which one is being picked up? Which signal line is being picked up for the mux? So what is the mux? Just really quick review on it. A mux, if I got 4 to 1 mux, which means I have 4 signal lines, it's going to pick up one of them as the output. So if I have four options, I need the 2 bits for the selection. That's why you are seeing S1, S0, right? S1, S0. Usually, you can definitely design the logic by yourself, whatever you want. But usually, if I have 0, 0 for the selection bits, which one is being picked up? The first one, right? So the first one will go to the output, will be picked up and go to the output. So that's the idea here. So if you look at the statement, the rules defined by this kind of syntax over here. So if S is 1, this guy is picking up, right? Being picked up. And if S0 is 1, D3 is being picked up. So in order to pick up D3 and send it to output, I need what kind of code for S1, S0? What's the code do I need for the selection bits, two binary bits, S1 and S0? 1 1, right? Yeah, 1 1. So 1 1. So S1 S0 when it is 1 1, D3 is being selected. All right. So if I'm asking you to do a 2 to 1 mux, it's even easier, right? I just need a one of them. I don't need a nested statement like this. I just need a 1, right? For example, just 1 like that, right? Any question on this? No. So I think you just, for the lab, you need to fill in all these crossed areas and generate the test bench and verify it on the FPGA. So I have a 16-bit running LED. Should be really simple, right? Just increasing this to 16 to 0 to 15 here. What else? Do we need to increase the number of counts or no? No, it's just a 1 second for each shift, right? Still 1 second, it's not changing. Do you want to change here? Yeah. Because the initial value for the LED must be a hex number, right? Otherwise, it's going to be too long. Or you can just type 16 binary bits over there, which is fine. So it's going to be 16 prime B and 16 binary bits. And for this one, it has to be LED. What? To what? And what?
15 to 0.
Yeah? Huh? Because there are 16 LEDs, right? From 0 to 15. So it's going to be like 14 to 0 and then 15, right? So the lower 15 LEDs need to be shifted to the left. So this becomes 14 to 0 and 15, right? Do we need to change anything here? Increment by what? By 1, right? If you want to shift it faster, what are the options? Instead of 1 second for each, you just want to do this, right?
Yes.
Like Christmas lights. Increment by 3, 5, right? Or here, you want to change here to a larger or smaller number. smaller number, right? So it's reaches a smaller number takes shorter amount of time. That makes sense? Okay? Alright, let's start working on it. I mean, for the tax for having issues, we'll look into that. I'm gonna send a request to the IT right now. See if it works.